Yeah, well, hello. Today we are gonna discuss about how Swiggy and other delivery applications such as Zomato or Zepto, Blinkit predicts how much time will it take to deliver a product to you from the customer, like from the restaurant or from the warehouse. So today we are gonna talk about Swiggy, and the same model works with Zomato as well, that how they work, and in some later video we will discuss how Zepto and Blinkit work. So have you ever seen a timestamp like this one when you go to cart value and you see a time that it's shown that yeah, within this couple of minutes the product will be delivered from the restaurant to you. So how does it actually work, and what are the challenges they have to face while building this technology to predict the exact time in which they will be they will uh, send that order or like deliver the order to the end user. Yeah, so they okay, they use a term which is, in generally we see it as promised delivery time, but in the context of technology, like in the context of their application, that is seen as promised service level agreement, or PSLA. So what it does is it is sort of a model which predicts uh, uh, not exactly a model, but instead an agreement which says that this is the output time, which is based on the multiple regression machine learning model that tells how much time will it take to deliver your product. Okay, so there's been a thing which we say, let's suppose that if there is a situation in this case, if the app shows lesser time and it in the real world, in actually it takes like more time than it shows on the screen, then that might lead to dissatisfaction of user. But if the application shows higher time, that it will take a lot of time to deliver the product to you, then there might be a possibility that user won't even place the order with you. So in between both of these situations, there's a period of time that is called Goldilocks zones. Okay, we can understand this with a very beautiful chart shown on this blog, in this blog, where if the time is too high, very few people will be ordering, because obviously they will just shift to any other app, or they might end up taking another route for getting the food. And if the time is too low, and in reality the time it takes to deliver the product is much more than the time it had predicted, then it will be a bad customer experience that might end up losing the application, like the application like Swiggy might end up losing that user. So in between that area, between both the times, there's a period that's called Goldilocks value, which is just enough to deliver the product without being delayed, and also without hurrying any either of like let's say without hurrying the delivery executive or our restaurant. Okay, so basically they we can see it here. There are downstream systems within Swiggy that get impacted by the promised delivery time of an order. Our assignment system takes this and take this time as an input and assign the right delivery executive to fulfill that what was promised to the customer. The customer care ecosystem also uses this promise to decide relevant action for the customer tickets. Our exception management start kicking if an order is getting delayed beyond the promised time. So let's say if an order is supposed to be delivered in 29 minutes, but it's already 21 minutes and it's past around 5 minutes. So let's say it's around 34-35 minutes, but the order is not delivered. So their exception management system kicks in, and it checks why isn't it not delivered yet, and what's the main issue. And if there is any genuine reason, then they start to communicate with the customer that yeah, this is the reason because of which your product is being delayed. Like in some time, sometimes you might have seen if there is raining outside, or if there is any traffic jam or an accident have happened outside, because of which the delivery executive isn't able to deliver the product on time. Then we got a notification, and sometimes even we got a call from like Swiggy that yeah, your order is delayed, and this is the reason because of which it is delayed, and we are very sorry for so like their grievance for the bad experience of ours. So this is what they are explaining it here. The efficiency of these system is directly dependent on the accuracy of our direct delivery time promise. So it it's not just that how much traffic is there during the final outcome, sorry, final delivery time, but there are a lot and a lot of other variables as well, which we will be discussing like in this video only. Okay. Okay, so here we can see the delivery times are impacted by number of different factors. The first one being type of restaurant. So let's say if there is there are mainly two type of restaurants. If the one is cloud kitchen and the another one is like traditional dining restaurants where users can a normal customer can go and sit there and eat from the restaurant as well, and also that same customer can order the food from either online, or they can directly call the restaurant and order place the order. So in that situation, the traditional restaurant takes more time to prepare the food because they have to serve three different segment of customers. But in cloud kitchen segment, there are only one type of customer which they are getting only from online platforms such as Swiggy, Zomato, and other. So the kitchen have a lot of less time in making the product, in packaging, and from getting they took very less time from getting the order to to handing that order to the delivery executive. And also it depends also on the number of items in the order. So basically, if there is a lot of orders, a lot of products in the order box, then it will also take more time to like bake the product or like cook the product, that's cook the order. That's why it takes more time. Also the kind of dishes in the order, let's say, yeah, it's a very good example that preparing a pizza will take more time than packaging an ice cream. It's exactly, let's say, if I have ordered a salad, a bowl of salad, and one of my friends have ordered a large size pizza, so obviously it is that making a salad is much easier and much time efficient than making of a pizza, so like preparing a pizza. So obviously it also depends upon the type of dish which the user is ordering, and also the availability of delivery executive in that area. So if there is a lesser delivery executives in that area, what I mean is that near the area of a restaurant. So if there is lower amount of delivery executives and higher amount of orders, obviously that will also impact the time duration of which the delivery time. Okay, but there are, if like there is a lot of delivery executives near the customer, near the restaurant, then obviously the delivery time will be reducing because the load on those delivery executives will be divided. And also the distance from restaurant to the customer. Obviously, once, let's say, once that restaurant have handed the order to delivery executive, but still the delivery executive had to travel to customer's house and send it and deliver it to them. So the distance also matters, and a lot of things like what are the route are they taking, in at what time the food is being delivered, like have been ordered. And also you can say like is there a good road or the bad kind of road, like there is a lot of path holes or manholes in the road or not. So like a lot of different variables work on together to make that one to give the input to that one machine learning algorithm, which we will be obviously talking about in the near future in this video only. Okay, so what are the metrics? Okay, yeah, here they use couple of matrices to actually make that machine learning model. The first one is mean absolute error. What it does, it's just the average absolute deviation of the prediction from the target. So what it does is it takes the target and makes the average absolute deviation same as it's they uses metrics name is bidirection compliance, and also, and the another one is egregious delay. So with the help of all three of them, they yeah, with the help of these metrics, they put the data in the machine learning model, and then with the help of those inputs, output will come. And how the machine learning model work, we will also discuss about it. So there are like these variables which we will keep in mind, so that we won't like fall apart when there's a short form in the comes in the near future. So O2A, it's just order to assignment time. So it's basically the time taken to assign a delivery executive a delivery for the order. Let's say I have ordered something, and the person in the and the application, the time it takes for application to assign a delivery executive for my order, it's the O2A time. The FM time is the first mile time. It's basically the time taken by delivery executive from where he is to uh, to the place of the restaurant where from where he will be picking up the order. Okay, and the wait time is the time where when the delivery executive have already reached the restaurant and is currently waiting for the currently waiting for the order to be prepared, so that it gets handed over to him. And the last mile time is, it's the time which the delivery executive takes to travel from restaurant to the customer's location. And what is O2R time? So basically adding all of these things makes the O2R time. So it's the order to reach time, time estimated for the delivery to reach the customer location. So adding all of them, we can say it somewhere here. Yeah, we can add all of them to get the order to reach time. So basically, it's the time from when the order is being placed to the order is being delivered to the customer's house. This is the time which we call as O2R, yani ki order to what is that? Just give me a second. Yeah, order to reach time. Okay, now we will be discussing about the model architecture which they use to build that machine learning model, which will be which will be which will be predicting the time taken to deliver the product. Okay, so for modeling these targets area, we are using Nemo. Okay, so this is, I guess, somewhat somewhat yeah, I guess this is somewhat uh, yeah, I guess a lot of us have heard a bit about the MIMO system, or the multiple input and multiple sorry, the multiple input and multiple output system. So basically, it uses a deep learning model supplemented with entity embedding. So what does entity embedding means? There is a lot of different entities. Okay, we'll see here. Entity embedding are a neat way to encode categorical variable with higher cardinality without running into the curse of dimensionality. So basically, in simple terms, we can say that without making our machine learning model without making letting the machine learning model hallucinate over a large amount of data. So that's what entity embedding means, that we are giving the data in such a formatted and proper way that that our model doesn't hallucinate or doesn't understand something different which we are not expecting it to understand. Okay, even though the debate on tree-based models versus neural network for tabular data is still ongoing, in our particular context, it doesn't require much debate. Okay, so it is saying that there are basically two type of machine learning models with two type of data structure using the machine while building the machine learning models. The first one is the tree-based model, and the second one is the neural networks. But they doesn't care about this one because they have been, as they've said here, from the years of experiment. With both tree and neural network based approach, we have realized a lot of gains in performance via entity embedding and flexible architecture. So without using the tree-based model or the neural network, they are talking about embedding and flexible architectures. Okay, so the next, we have already talked about the embedding sections, entity embedding, sorry, entity embedding. Now let's say how Nemo work. So there will be some numerical feature, and then okay, how will it will work? That this will be the categorical level. This will be the inner level. So with the help of these data, like there are multiple sort of incoming data, and with the help of these, it went to a hidden layer one, and then again another hidden layer, which will let the data to output into multiple sources. So it works as well. It works this way कि the multiple input and multiple output network takes in multiple type of input such as numerical, categorical, and has multiple output nodes as well. So all the output shares the common set of input and number of hidden layers before branching out to their own sub networks. So this is how the total concept of Nemo works. Okay, okay. So the next we discuss. Yeah, this is a very good example how it actually works. It says it would require a feature of underlying legs O2A, FM, WT, and LM. O2A basically is order to what was that? Yeah, order to assignment time. And FM is first mile time, WT is waiting time, and LM is last mile time. Have a combined network lets the model learn the relationship between these outputs. So as I told you that adding up all the data will be the O2R. In addition, training a MIMO network along with the embedding helps embedding capture the semantics of interaction between different input much better. Okay, so it's just saying that the more amount of data we have, the more better we will be, the more better we will be able to predict it. Okay, it's the same thing. Here they are saying like they are considering a small example, and then telling, okay, one more thing, one more interesting thing is used by Swiggy and Zomato to do a cost cutting, or you can say the cost optimization in professional terms, is that let's say uh, a order takes 15 minutes to prepare. Okay, that order A from the restaurant, let's say it's RXA, the nearest delivery executive to restaurant is 10 minutes away, and the order B is from or RXB. There are five delivery executives standing outside of the RXB. So what will happen is that the exact moment, mm, the exact moment or within the first 5 minutes when the order A is placed to the RXA, the application will send an request to delivery executive that hey, took this order from that restaurant and they'll send the location of that restaurant to the delivery executive so that he can do a 10-minute ride, and in the meantime the food is being prepared as well. But in the second case where five of the delivery executives are waiting just outside of the order waiting outside of RXB and restaurant B, so in that situation what will happen, just before the 15th minute time or just around the 15th minute time, the application will send a request to all of them that hey, we want to send this order from here to that other to the like customer's location. So if any one of them chooses accepts the request, then they will be then that data will be sorry then that delivery executive will be handed the order, and he will now be forwarding that like delivering the product to the end user. So this is a very basic diagram where this node tells here order is generated, and the meantime the food is being prepared. The application look for the delivery executive. Here find the delivery executive. This is the first mail time where he's going to the restaurant, and once he reach the restaurant, he's waiting until unless the order is being prepared. Once the order is being prepared and handed to the delivery executive, it is then perform its last mile time and reaches the customer. Okay, so this is the total journey of how a order is being placed to how it ends up in our plate. Okay, and one another example here is that the target value exhibit a mix of regression and time series like behavior. For example, let's consider the delivery executive time from restaurant to customer location. In general, this time will show hourly and weekly seasonality, where the travel time, let's say, for let's say Saturday 9 p.m. for a given customer, and restaurant location will be similar to the previous week timetable. This is also a recency factor that's important in generally for constructing features. We use historical as well as near time. Okay, so basically what it says that uh, uh, let's say it the algorithm also took the day and the time, and if let's say the same at around the same time and some other day there are orders in that region. Let's say today is Saturday, and in the 5 a.m. morning a video order is being placed. So to predict the timing for order to be to reach to my destination to reach the customer's location, it uses the data for the previous day and the previous day and the previous day and the day around it and also the time around it. Let's say that if I've ordered the at 5 a.m. in the morning, it will take time from 4 a.m. to 6 a.m. and uh, and send that data to the machine learning model, and that model will then like format out the data and uh, like check out the valuable data from those set of data. Okay, so the next thing is food preparation feature. Okay, so to account for the assignment engine behavior, we consume the same prediction as an input to the food delivery time prediction model. Yeah, exactly. It's the same thing that we've told you, that it depends upon the type of item, the number of items, and the load on the restaurant at the particular moment the order is being placed. Okay. It also depends upon several factors such that streets at the moment restaurant as derived from orders placed and order prepared by the restaurant in the recent past. So it not only checks that how much stress is currently over that restaurant, it also checks how well it have performed in the past when it have a lot of orders. Also the size of the order, like what are the number of the order, the total number of the order, what are like unique or different items, also the past preparation time behavior of the restaurant with respect to the item in the orders, the items in the order, as I've told you already. And now comes the assignment and the first mile. Okay, so what happens when the order is assigned to a delivery executive and he have to travel the first mile? Here there are a couple of things which the application took into the consideration is that stress in the system, what how much actual delivery executives are available and how much actually delivery executives are active at that time. Okay, and it compares them with the how much active orders are running over the application in that same region. Let's say there are only 10 delivery executives in a 5 kilometer radius, but there are almost 15 or 20 orders. So the stress on one delivery executive is around 3 to 4 orders. So it will be very hectic for that delivery executive, and that will eventually add up in the delivery time to of the food to the end user. Okay, also the historical assignment time and first mile behavior of for the restaurant and the operation zone as a measure of the general behavior, as I already told you that these things also take into the consideration near real-time behavior for the restaurant and the operation zone as a measure of the deviation from the general behavior. Okay, so it's almost the same thing. It's but the twist here is the second point, take the historical data and at here it takes the near data. Let's say if I've ordered at 7 p.m. in the evening, so it took the data from 6 p.m., from 5 p.m. as well, that what are the history of the data and what are, sorry, of that restaurant, and what are the history of the area, what are the number of orders being prepared, what are the number of orders being prepared from that restaurant, and what are the number of order being delivered to your area from that region. So a lot of these inputs and parameters are being sent to the machine learning model that will eventually give us the time at the end. Okay, now the mile feature will have last mile distance, how much distance is from the restaurant to the customer's location, historical speed patterns around the customer and re- uh, restaurant location. So let's say if there are a lot of potholes and not a good condition of road, or there are like not a like a lot of traffic around that region, around that route on which that customer's location and the restaurant location is being placed. So if these things aren't good and aren't managed properly, it will eventually result in increased time for the delivery and also the near real time speed patterns. So let's say uh, if someone is placing an order in the office rush time, let's say if someone is placing the order at 6 p.m. in the evening, it's very obvious that in metropolitan cities or even some other cities as well, if a delivery executive is having your order and is coming to your location, then obviously it will take more time because of the traffic, ongoing traffic in the on the road, because of just the like off time of the what we say the offices. Okay, so what are the final result which we see? Moving to a MIMO network design with shared input and hidden layers helped to reduce the training memory footprints by 50%. So from discussing about what to choose between trees and neural network, they have choose the MIMO network design, which have reduced their memory footprint by 50%. And also they have shared the optimization of interdependent outcomes, which is nearly 30% improvement in the MEA for O2 prediction, which is if in this term we talk about, this is a very very huge number. Okay, and also the introduction of in-model embedding helped the overall ME, the O2R time by 5%. So while using this sort of model, the MIMO model, they have reduced the overall time of the delivery time by 5%. And when we are talking about 5%, it might not seems big to the end user, but for a company, for a huge company which have millions and millions of orders, like at least hundreds of thousands of order every day, they are like uh, delivering every day this much amount of data, this much amount of orders to the customer, then 5% is a very big number. It's literally a very big number. So what are the next steps? But here comes the main thing which I have, and the most important thing which I have learned uh, in this research paper, is that a good machine learning model is the huge amount of data required. Okay, but these are all things. There is still one issue. This research paper have a lot of data, but in the real world, we know that um, the data is not uniform. The data is not equally divided throughout the country. Let's say the amount of traffic uh, in Bangalore and the amount of traffic in Mumbai, the amount of traffic we see in Gurgaon, and the amount of traffic we see, let's say Noida, or the amount of traffic we can say see in Pune, in Indore, in Bhopal, they are a lot different from each other. Mumbai, Bangalore, and Gurgaon will have the worst amount of traffic, uh, so the delivery time will be larger. But in Indore, in Bhopal, uh, the roads are good. There are not so much traffic going on, so the delivery time will be lesser. But we understand this, but the machine learning model doesn't understand. What machine learning model understand is just this that huge amount of data. So but the issue with Bhopal and Indore is that there isn't enough amount of people in Bhopal and Indore who are ordering, that they got a huge amount of data from their orders. So this is one of the issues on which the Swiggy is actually working on right now. It says the cohort like in data also tend to lag in accuracy of predictions. So the larger the amount of data uh, it eventually results in the better the accuracy of the output. Okay, so and after that, in addition to these sparsity issue, there's also the issue of standard loss function being one size fits all approach to modeling. In our upcoming work, we'll be looking at. Okay, so this was the main issue which they are now facing and they are now working on. But uh, in this research paper, we not exactly the research paper, but yeah, in this vlog, we actually understand how the machine learning model, how actually the Swiggy predicts the food delivery time of an order to the customer, and it has so much in depth. But in some another video, we will discuss it more about how Blinkit and Zepto works because they have their own dark stores. So they do not have to wait for the restaurant to prepare the order. They have like some very unique way of handling these things, and that's also a very good case study to work to see on. Thank you very much.